Okay, so any questions on the last time? I mean, last time what did we do? I think in the end we discussed about the orthonormal basis. How in the orthonormal basis, everything becomes much simpler, right? For example, a Hermitian operator means really the matrix representation itself is Hermitian in the usual sense, right? In the usual sense being that adjoint is simply you take the transpose of the matrix and complex conjugate, right? And indeed, in the orthonormal basis, that's what is a definition of adjoint operator, right? So everything goes fine. Okay, now let me go back to the eigenvalue equations. You remember we discussed, I think 2 or 3 lectures back, the notion of eigenvalue. So given an operator A, we consider this equation A acting on some state, say V, is equal to some number, complex number in general, V, right? This was the eigenvalue equation, which, I mean, so if you can find a solution for this equation, I mean, A is given to you, this operator is given to you, okay? And if you can find a solution to this equation for some lambda, lambda is some complex number, right? Then you say that V is an eigenvector of A with eigenvalue lambda. Usually what I will do is that I will just because, I mean, clearly which eigenvector appears here depends on the lambda. If I choose a different lambda, I will get a different, if a solution exists, it will be a different solution, right? So I will usually just indicate it as lambda itself, to indicate, or no, let me not confuse it. I mean, that may be confusing, okay? Let me just leave it as it is. Okay. So this equation, of course, I can rewrite, I mean, take it on the other side. This is the same as A minus lambda times the identity operator acting on V equal to 0, right? But when I say 0, I mean null vector, the null vector. Okay, so this equation, I mean, can be rewritten in this way. However, we also said, in fact, I gave you an example to show that you cannot always, I mean, you can generalize this notion, right? So there's something called generalized eigenvector, which satisfies the equation A minus lambda E to the power of some R acting on V equal to 0, where R is positive, R is some positive integer. But A minus lambda E to the power of R minus 1 acting on V is not 0, right? So this can happen. I mean, there are situations where you have, I mean, some vector V which satisfies this equation for some positive integer R, right? In such a case, you say that this eigenvector V is of rank R. Okay, so this R is called the rank of that eigenvector, generalized eigenvector. Of course, from this point of view, the usual eigenvectors are simply R equal to 1 case, right? So these are simply R equal to 1 case, right? Because you just put R equal to 1 here, you see. Okay. Then, okay, we also proved something that if the operator is Hermitian, for Hermitian operators, I'm just trying to remind you because this was a few lectures back. For Hermitian operators, all eigenvectors are of rank 1. Actually, we proved several things for Hermitian operators. All eigenvectors are of rank 1. Second, eigenvalues are real Do you remember this proof? Yeah, you remember that, okay. And one more thing you can prove, and I'll just prove that. One more thing you can prove is that two eigenvectors with different eigenvalues, so different, right? That's important, different eigenvalues. So which means lambda is different for the two cases. Eigenvalues are orthogonal to each other. Huh? So how do you prove that? Let me just prove this. I think this I didn't prove in the, before. So let's consider the case. So let me call the operator as H, Hermitian operator. This is Hermitian. And I have two different eigenvectors. Let's call it V1 with eigenvalue lambda 1. And another, let's call it V2 with eigenvalue lambda 2. Okay, where we are saying that they're different, so lambda 1 is not equal to lambda 2. Okay, so let's do the following. Let's take the first equation and the second equation here. First equation, and take the scalar product of on both sides with the V2. Okay, so you just apply V2, dual vector V2 here. So you get here V2 H V1. That's equal to lambda 1 V2 V1. Right. The second equation you multiply by V1, the dual vector V1. So you get here V1 H V2 is equal to lambda 2 V1 V2. Okay. Now let's take the complex conjugate of one of these equations. Let's say this equation. I take the complex conjugate of that. So take the complex conjugate. Of this equation. So you get here complex conjugate of that, but that is the same by using the definition of adjoint. That's the same as V2 H dagger V1, right? This I've used the definition of the adjoint. Okay, you take the complex conjugate of that, then that's the same as by definition this. And the right hand side is simply lambda 2, because lambda 2 is real, because it's Hermitian, so both are real. So complex conjugate of lambda 2 is itself, and then the complex conjugate of this, but that is just the V2 V1. Okay. Now use the fact that H is Hermitian, so H adjoint is it's equal to H, so you can remove that, right? And now compare these two equations. You see the left hand side of these two equations is the same, so right hand side must be equal, okay? But lambda 1 is different from lambda 2, so the only way that can happen is if this is 0, right? Because again, I mean what this equation says is that lambda 1 minus lambda 2 V2 V1 is 0, right? This is what it, combining this equation with that equation, you get that. But since this is not 0, therefore the only way this can be satisfied is if this is 0. So this implies V2 V1 is 0. So they're orthogonal. That's an important point. So this is true for Hermitian, not in general, because we have used the fact that this is Hermitian everywhere, right? Okay, so today now what I will do is try to prove that, okay, as I said, we are really interested in Hermitian operators. I mean, for physics, we are really interested in Hermitian operators, right? And what I will try to prove is that Hermitian, I mean, once you choose a basis in n-dimensional space, let's choose orthonormal basis. So we have a Hermitian matrix, right? Which means when you say Hermitian, it means its transpose complex conjugate is equal to the original matrix, right? So what I want to prove is that Hermitian matrix can always be diagonalized, right? Meaning you can choose some orthonormal basis in such a way that the Hermitian matrix can be diagonalized. I mean, yeah, right? So for this, I need to, unfortunately, I mean, the proof is, I mean, if, okay, let's say, if you assume one fact, then the proof is almost trivial, okay? And that the fact is the following, that if you assume that you can choose a basis for your, I mean, the space, vector space, which consists of eigenvectors of the operator, okay? That's not obvious at all. What it, I mean, what that statement is saying is that any vector can be written as a linear combination of eigenvectors, right? That's what it means. If you say that eigenvectors can form a basis, that means that any arbitrary vector I can write as linear combination of the eigenvectors, right? If you assume that, then the fact that Hermitian operator can be diagonalized becomes completely trivial. But that's a difficult thing to prove. The difficult thing to prove is that you can choose a basis consisting of eigenvectors. So unfortunately, the proof is a bit long, but try to follow that. The reason why I wanted to, initially I thought maybe I should not give the proof, and I just state this result. But I wanted to give the proof because the steps involved in the proof are themselves very interesting, right? So it's good to know those steps. Okay. Okay. So there is a. So let's again look at. Again I go back to arbitrary operator, not just Hermitian. Any matrix. So take any matrix. So this is an n by n matrix. Okay. Okay. A, and consider the following equation. Let me just use the E. E means, okay, let me use 1. Doesn't matter. So this is n by n unit matrix. This is an n by n unit matrix. And compute the determinant of this. Okay. Maybe it is convenient to write, more convenient to write like this. This minus A. Okay, it doesn't matter. That's up to a sign, it's the same. Okay. So this is an n by n matrix with I have multiplied by lambda. Lambda is arbitrary complex number. Okay. And A is the whatever the matrix is, whatever matrix you have started with. And so this will be also, this whole thing is an n by n matrix, because this is n by n, that's n by n, and n by n matrix, and you just compute the determinant of that. Okay. So what is this going to be? This is going to be some polynomial in lambda, right? It will be, in fact, let me use the same symbol that I used here. I think it's they use a symbol phi in subspaces. Yeah, phi lambda. So this I just call it phi lambda. Phi lambda is a polynomial in lambda, and of what degree? A degree n, right? So because if you just look at that, I mean, what is the structure of this matrix? This one simply is lambda, 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 all the way. There are n by n, right? So there are n entries here in the diagonal. And then you have A, so this will be minus A11, A12, etc., right? Minus A12, minus A21, minus A22, etc. Okay, but so I want to take determinant. So in particular, in the determinant, there will be one term which will be product of all these diagonals, right? So that will involve lambda to the n also. There will be a term which will be lambda to the n, right? But that's the maximum. You cannot be more than that, right? So this will be nth degree polynomial. In fact, it looks like, it starts like lambda to the n, and then lower order terms. Some coefficient times lambda to the n minus 1. So maybe let me write it in the same way. So it will be of what form? It will be some, it will be some, so lambda to the n plus, let me call it phi n minus 1, lambda to the n minus 1, plus phi n minus 2, lambda to the n minus 2, all the way up to phi 0. I mean, phi 1 lambda plus phi 0. It will be generally of this form, where these will be some numbers, right? And those numbers will depend on all these numbers, A11, A12, all these numbers, right? So given a matrix, you of course know these numbers, and those numbers will enter here, right? So these coefficients will depend on those numbers. But there are some numbers, some fixed numbers. So now, so what, I mean, if you want to solve for this, so I mean, you can think of this as it's an nth degree polynomial, and you can find, I mean, there will be n solutions, n roots, right? So if you set this equal to 0, then it will have n roots. In general, complex roots. I don't know, I mean, if you know this theorem, that if you give me an nth degree polynomial, I mean, if an equation of this type with an nth degree polynomial equal to 0, then there are precisely n solutions, n complex solutions in general. Okay, sometimes if you're lucky, it can be real solutions, but in general, it will be complex solutions. I just accept it for the time being. In the second chapter, I will prove it. When we go to the complex analysis, there's a very elegant proof of this theorem. But at the moment, let's just assume that. So there will be, so there exists n solutions of this equation, of of this equation. Okay, and let me just call the solutions as lambda I, where I goes from 1 up to some let's say k. But you see, the solutions may not be different in general, not all different. There could be multiplicities. I mean, the same solution may appear several times, right? What we call degeneracy. There could be degenerate situations. So in general, so the lambda I may appear, let's say Ri, let me not use the Ri because that was, okay, let me use the Ri number of times. So multiplicity of this is with multiplicity. So lambda I comes with the multiplicity Ri. Okay. So what it means? It means that this phi lambda, I can rewrite it in the following way: lambda minus lambda I to the power of Ri, product I goes from 1 to k. Right? That's what it means. That's what I mean by saying that. So you see, when lambda equal to lambda I, this is 0. Right? That's what we're looking for, the solution. Right? Is that clear? I mean, we are looking for a solution phi lambda equal to 0, the equation, right? So when I'm saying, so what do I mean by the statement that it has a solution lambda I with multiplicity Ri? It means that this phi lambda appears, phi lambda can be rewritten in this form, right? Indeed, notice that when lambda equal to lambda I, this becomes 0. So that is the solution of this equation, right? And it appears Ri number of times. That's what I mean by multiplicity. But of course, you of course realize that sum over Ri, I going from 1 to k, should be equal to n. Correct? Because I mean, after all, this is an nth degree polynomial. Is that clear or not? It's clear to everyone, right? Do it again. I mean, so in general, I mean, if you take this nth degree polynomial, and if I found there will be n solutions, as I said. Some of them may appear with some multiplicities, right? So in general, it will look like I can always rewrite this as lambda minus lambda 1. This may appear, the same root lambda 1 may appear several times. No? So lambda minus lambda 1, lambda minus lambda 1. So R1 number of times. Okay. Then lambda minus lambda 2, lambda minus lambda 2, etc. R2 number of times, and so on, all the way up to product. It's all taking the products. Finally, lambda product, lambda minus lambda k, Rk number of times. Okay, that's what that notation means. It's a product. I'm taking the product. Now, if you look at this, what is the highest power of lambda which is appearing here? You see, if you just take the lambda, you take the product, you have to open the brackets, but take the highest power of lambda. That will just come from the taking this product lambda, lambda, lambda product, right? So from this one you get lambda to the power of R1. From this one you get lambda to the power of R2, and so on, all the way up to lambda to the power of Rk. So the highest power that you will have is lambda to the power of sum over Ri, right? But we know this is highest power is n. So that's why this equation sum over Ri, I going from 1 to k is this range. Equal to n. That's just a statement that this is an nth degree polynomial. So really there are n roots. It just happens that some of them are appearing with multiplicity, so I call them R1, R2, etc. Of course, they could be 1 each. If all the roots were different roots, then each of these Ri is equal to 1, right? But it may not be. Depending on the matrix A, sometimes the roots may have multiplicities, degeneracies. Okay, so that's it to take into account. I put that. All right. Yeah. In general, complex numbers. Yeah. Of course, for Hermitian matrix, it will be real. Okay. Now there is a very important theorem which goes under the name of Cayley-Hamilton theorem. Cayley-Hamilton theorem, which says the following: take this phi lambda, and just wherever you see lambda, replace by the matrix A itself. Okay, So let me define phi of A. You see, this phi is a function of lambda. Lambda is just a complex number, right? But now I'm going to replace lambda by the matrix A. Okay? So what it means, this is nothing else but A to the power of n plus phi n minus 1, A to the power of n minus 1, and so on, all the way up to phi 1 A plus phi 0. But phi 0 is not coming with lambda, but each of these things is an n by n matrix, right? So this better also be n by n matrix, right? So but phi 0 is just a number. So what I should do is I should also take phi 0 times n by n unit matrix. So this is what my definition of phi A is. So take this character. This is, by the way, this is called characteristic polynomial. So let me just give some name. I mean, you might hear these names: characteristic polynomial. Okay, this phi lambda is called the characteristic polynomial, because it's a characteristic of A, of the matrix A, right? Because once you specify the A, it just gives you this polynomial. Now, what we are doing is that we just replace these lambdas by A, and the last one, which comes with just 1, you replace by identity matrix. So that is by definition phi of A. So of course, this notation, you know, I mean, A to the n means take the matrix A times A times A n times, and just to take the matrix multiplication, right? Just keep multiplying this. That's what. Okay. Now the theorem says that actually phi of A is identically equal to 0. It's a 0 n by n matrix. That's a. So this is just a, I mean, n by n matrix with just a 0, 0 entry. Everything is 0. Okay. It looks completely miraculous, but it's a fact, you know. Huh? No. That is just to find the roots, right? I mean, now I just keep this is an arbitrary function of lambda, but if I want to find the roots, then I set it equal to 0, and then once I have found the roots, then I can rewrite this polynomial as simply product form. I equal to 1 to k, this to the power of ri. So this polynomial is identical to that. That's okay. So how does one prove that? So yeah, the proof is the following. You take again this matrix, no? Lambda times the identity matrix minus A. This is an n by n matrix, right? I mean, it will have some whatever the entries and so on. So let me define. You remember this when we defined the inverse matrix. We had to first compute the cofactor. I don't know. It's called cofactor, right? I mean. So what you do, you take this is an n by n matrix with some entries here. Let's say I look at the ith row and jth column. You just remove the ith row and jth column and take the determinant of the remaining part, right? So the remaining part will be n minus 1 by n minus 1 matrix. Okay. And then, so you define, so that is what is called the cofactor. I think it's called cofactor. I'm not sure if, I think it's called cofactor. Huh? What is it called? Adjoint cofactor. I see. I mean, yeah, there's some, right? So, and then you have to multiply by, to compute the inverse, you have to multiply by minus 1 to the power of I plus j, right? And then take the determinant. So determinant of, what shall I call? So this determinant of this n minus 1 by n minus 1 matrix, which is obtained by deleting the ith row and jth column, right? And let's give it a name. Let's call it GJI. Okay, because of course this number will depend on which row and column I am deleting, right? It will depend on that. In fact, this is the way you construct the inverse, right? The inverse of the matrix is basically given by these numbers divided by determinant of the matrix itself, right? But I don't divide by determinant, I just keep it as it is, just the cofactor. Okay. So this will be a function of lambda, right? Because you have, right? And in fact, you can see what will be the highest, what will be the degree of this polynomial. Okay, it can at most be n minus 1, right? It can at most be n minus 1 polynomial. Degree polynomial. Yeah. Okay. So let me write it like this. So this guy. So this is then you construct a matrix. Okay. So define a matrix G, whose elements are just the Gji. You understand? I mean, so this will be again an n by n matrix. So here it will be G11, G12, G1n, Gn1. So arrange them like this. So given this polynomials, you just put those polynomials here, okay, inside. So this gives you an n by n matrix. Okay. So this will be an n by n matrix. So I can actually rewrite this as we said, each of these numbers are at most of degree n minus 1 in lambda. These are not numbers, these are functions of lambda, of course, right? Each of them is a function of lambda, each of these entries. But each of them is at most of degree n minus 1, so I can expand it into as let's see, use the index G m, okay, lambda to the m summed over m going from 0 up to n minus 1, where each of these are n by n matrices. These are n by n matrices. Yeah.
I can't get clear where the G is coming.
So what am I doing? So this is the matrix. The lambda 1 minus lambda times identity minus a is some matrix here, right? I mean, this is the precise form, lambda minus a11 minus a12. This will be lambda minus a22, etc. Right? This one. Now, what you do? You take the ith row. I is between 1 and n, right? Ith row and jth column and delete them, remove them, right? Then the result will be a n minus 1 by n minus 1 matrix, right? You take the determinant of that. That is what I call. So this is what. So I take this I remove ith row and jth column, and then compute the determinant of that resulting n minus 1 by n minus 1 matrix, and then multiply by minus 1 to the power of I plus j. Okay, this is what I call it. I call it Gji lambda. Okay, I just give it a name. This is going to be a polynomial of degree maximum n minus 1, right? I mean, take for example, suppose I equal to 1, j equal to 1. Okay, then I'm removing the first row and the first column. So then this lambda minus a11 has disappeared, right? And the remaining n minus 1 by n minus 1 matrix can at most have lambda to the n minus 1 power when you compute determinant of that, right? So this is what. So this will be some polynomial of maximum n minus 1 degree. Okay. And then I just rearrange. I just put all of these things in the form of a matrix. So that will, since I and j go from 1 to n, that will give me a n by n matrix. Okay. Now each of these entries inside here is a polynomial of degree maximum n minus 1 in lambda. So I can expand. I can rewrite this matrix in the polynomial expansion, where these are now n by n matrices, the coefficients are n by n matrices, and then lambda to the power of m, where m goes from 0 to n minus 1. Yeah? Okay. Now let's take this. So this matrix G. So this is a matrix G of lambda. G is a function of this is an n by n matrix, which is a function of lambda. Now let's multiply G of lambda with again this matrix lambda times identity minus A multiplied on this side. Okay. This is let me call it h of lambda. Okay. When you multiply this, what am I going to get? Remember, as I told you, this is if I had divided this by the determinant of this original matrix, that would have been the inverse of this matrix, correct? I mean, this is how you construct the procedure I mentioned. You remove the ith thing and the jth column and this cofactor that you compute, right? That is exactly that divided by the determinant is the inverse of the matrix, right? But I'm not dividing by the determinant. So when I take the product of these two, that is going to simply give me determinant of so it will give me the identity n by n identity matrix times the determinant of the original matrix lambda identity minus A. Right? So again, let me repeat this step. If I had divided this object by determinant of lambda minus A, okay, then this would have been exactly the inverse of that matrix. Right? So if I had divided both sides by determinant of lambda minus A, this would have been the inverse. But then if it was the inverse, then this times that should be identity. Right? But in this construction, I didn't divide by determinant. So that's why I have this determinant here. Okay. But now, you see, if you look at this expression, now if you replace this lambda by A, this is identically 0. Right? I mean, after all, what is the form of this? This we said, this is some gm cross times lambda to the m. This is the sum n by n matrix. Okay. Then I multiply this to this lambda times identity minus A. Okay. And I have summation over m equal to 0 to n minus 1. This is what it is, right? Now what I'm saying is just replace wherever you see lambda, replace it by A. Okay. So, but when you do that, so now replace lambda by A. Okay. Then you get here gm n cross n matrices m equal to 0 to n minus 1, and then here you get a to the power of m. Okay. And here you get a times identity minus a. But this is 0. This is a minus a. So you get already a 0 matrix, n by n matrix, and then whichever matrix you multiply it to a 0 matrix, again it's a 0 matrix. So left hand side is 0, therefore the right hand side must also be 0 when you replace lambda by a. Okay. So I mean this is nothing else but the phi lambda. This is what I call phi lambda, right? So this is the phi lambda. Okay. So when you replace lambda by a, since the left hand side is 0, the right hand side must also be 0. So this is the proof of the Cayley-Hamilton theorem. Looks quite amazing actually, right? That you have this characteristic polynomial, just replace lambdas by a, and the answer is 0. You know, it's as a matrix, so you know it's quite surprising, but it is true. I mean, you can try. You can just play with some 2 by 2 matrix. No, 2 by 2 matrix. It's this quadratic polynomial, right? And then just work it out for just to choose some arbitrary numbers for the 2 by 2 matrix A, and then try to see if this is true or not. Okay, this has a very powerful. So is that point clear now? I mean, this proof. So the proof is simple. I mean, the procedure is this. I mean, you take this matrix lambda, this guy lambda 1 minus a, and you want to you construct G, which is basically the cofactor matrix for that, right? Which is part of the for the inverse would have been the cofactor matrix divided by the determinant. But I'm not dividing by determinant. Just take the cofactor. Then this times that should be the determinant times identity matrix, right? But then now you replace lambda here by a, then you get left hand side is 0. So this also must be phi of a must be 0. That's the 0 matrix. Huh? So that's the basic statement. Okay. So now what we will do is again another quite a beautiful step. Let's consider 1 over phi lambda. Okay. Well, this is, as we said, phi lambda is simply this 1 over lambda minus lambda I to the power of Ri, product I goes from 1 to k. Right? Now, you know that you can always, there's something called a partial fraction. You can rewrite it as a sum of fractions. So this I can rewrite it as 1 over lambda minus lambda I to the power of Ri summed over I from 1 to k with some polynomials here which will be depending on this Fi lambda. What is Fi lambda? This is the polynomial of degree at most Ri minus 1. Right? This you are familiar with that, right? I mean, just take a simple example. Suppose I have just 2 by 2, 1 over lambda minus lambda 1, 1 over times lambda minus lambda 2. Suppose it was just n equal to 2 example. And okay, and let's say there are 2 different eigenvectors, eigenvalues. So then I can write this as 1 over lambda minus lambda 1, I mean some number, let's say alpha plus beta lambda minus lambda 2, and we can determine alpha and beta, because again just take the common factor. So if you take the common factor, this expression is the same as lambda minus lambda 1 times lambda minus lambda 2, and this will become alpha times lambda minus lambda 1 plus beta times lambda minus lambda 2, right? You equate the two sides. Here it is 1. So clearly this lambda must cancel. So beta must be equal to minus alpha. So beta equal to minus alpha. So lambda will cancel. And then you have, and then what is left over here is alpha times minus lambda 1. And you see beta is minus alpha. So it becomes plus lambda 2. Okay. Then you just choose alpha equal to 1 over lambda 2 minus lambda 1. Right. So this expression is simply 1 over lambda 2 minus lambda 1, and this minus that. So you see, and this can be done for arbitrary. If you take, for example, another case where say this is square here, and that is without a square. Right? In that case, if you can again try to write it, it will be like this. It will be lambda minus lambda 1 square, and then here there will be not a number now, right? It will be actually some, let's say, alpha lambda plus beta, okay, plus here gamma lambda minus lambda 2. You can write like that, and you can again compute alpha, beta, and gamma by taking a common factor. Then you see when you take the common factor, you have this times that. Okay, so this is linear in lambda. That is linear in lambda. So this will give you a quadratic in lambda. And then when you, and then plus this times that is also quadratic, right? So now you see you have what you want to do. You have to remove the lambda square term because there is no lambda square here. You have to remove the lambda term, and the constant term should be 1, right? But you have three unknown quantities, alpha, beta, gamma. You can determine alpha, beta, gamma by these equations. Okay, so this can be done. Okay, of course, if the n is large, it will take you a long time to do this computation. But in principle, this exists. This decomposition exists. It's guaranteed to exist. Huh? Okay, so here it's we have this. So there will be always, you can always write it like this. In this, I think it's called partial fraction, right? Expanding in partial fractions. Okay. Now let's multiply this equation by phi lambda itself. Okay. So the left hand side is simply 1. So let me write multiply this equation by phi lambda. So left hand side becomes 1. And the right hand side is simply I equal to 1 to n, 1 to k, fi lambda. Now you see the phi lambda is this whole product. And now when I'm multiplying that, what will happen? This factor will get removed, right? See what I'm doing. I'm multiplying this whole expression now by product lambda minus lambda I. Let me put here j. Rj, j going from 1 to k, right? I'm multiplying that. So when I multiply it each of these terms, for example, suppose I multiply the ith term here. I mean, this is a sum, right? So multiply by to the ith term, then and this thing, then what's going to happen? Just the ith term will cancel, right? But all the remaining terms will survive, right? So here you'll have this times a product j going from 1 to k, but j not equal to I. Okay, just the ith term gets removed, gets cancelled, and what is left over is that. Okay, it all looks empty exercise, right? I mean, after all, I just started with 1 over phi lambda and I just rewrote it in this form, and then I multiply again by phi lambda, so you get identity. I mean 1 here, but that is giving us some conditions on this fi lambda. That's what it is doing, right? It's saying that fi lambda must be such polynomials such that this sum is equal to identically 1, identically. For any value of lambda, this should be identically 1, right? So this is an identity. Okay. Now, if you look at this expression, we said this guy is a Ri minus 1th degree polynomial, right? Now, this one, you see here, it's an entire product, but except j is not equal to I, right? I mean, if I had taken the full product, it would have been of degree n, if I had included also the I, because then it is the phi itself, right? But I am removing from that the ith term, but the ith term it would have given you lambda to the power of Ri maximum, right? So this will be a degree, I mean, yeah, this will be degree n minus Ri, this part, right? But then to that I am multiplying something which is of Ri minus 1. So this will, the degree will be that, which is equal to n minus 1. So each of this term will be at most of n minus 1 degree polynomial, okay, for each I. R equal to 1 to k, I equal to 1 to k, sorry. Okay, so now why is one doing all this? Because this will actually give us some very nice operators which will project essentially arbitrary state into generalized eigenvectors. That's what it will do. So this is the intermediate step, but you'll see in just a minute. Okay. So let me give it a name. Let's call this guys as let's give it the same name as is written here. Yeah. So let's call this this whole thing as phi I lambda. Phi I lambda. I'm just giving it a name, not so that I don't have to write it all the time. This long expression. So phi I lambda is simply that. Right? So therefore, what we are saying that this equation. So this is phi I lambda. So we are saying that that equation is simply phi I lambda sum I going from 1 to k is equal to 1. That's what that equation is saying, where phi I lambda is that. So now let's again do the same thing. So this, as I said, phi I lambda is of degree n minus 1 maximum, some polynomial lambda. Let's again, wherever you see lambda, you just replace it by a. Okay. So let's define phi I a. Okay. Then what this equation is saying, because remember this is true for this is an identity. You see, it's not. This is true for any lambda. It's an identity. Okay. This equation. So I just replace lambda by a. Then again, this should be identity. Okay. So we are saying that this sum over I 1 to k is, remember, when we replace lambda by a, we replace the constant by identity matrix, right? So here is a number I just replaced by that number times identity matrix, but this number is 1, so it's just identity matrix. Okay. Now these are all n by n matrices. Each of these terms is an n by n matrix. So this is the very important identity we are getting. So what we are saying is that these are some n by n matrices for each I, but the sum of these matrices I going from 1 to k is equal to identity matrix. Okay. So that is the result of that. Now, so why are they important? So let me come to that. Why are they? As I told you, what we'll show then is that this will basically project any vector into a generalized eigenvector. Okay, I will. There are a few steps in proving that. So the first important point is, if you take phi I a and times phi j a, so I and j, I mean, are between 1 and k, and so there are two possibilities. One, when I is not equal to j, okay, when I is not equal to j, in that case, it turns out to be 0. 0 as an n by n matrix. Each of them is n by n matrix. Okay. And when I is equal to j, then it is simply phi I. Okay. So how do we see this? So let's take first the I not equal to j case. So remember the form of the phi I a. Phi I a was fi a. Fi was a function of lambda. I just replaced. Yeah. No, n by n matrix. Yeah, because A is n by n matrix, right? I mean, so remember, so yeah, this is an n minus 1 degree polynomial, right? So that means that this will have some form phi I, let's say, what shall I call A, lambda to the power of A, where A goes from 1 to n minus 1, right? But I'm replacing each lambda by A, so this each of term will be n by n matrix, right? So what was this thing? This was fi a times the product a minus what was phi I lambda was that, right? Sorry, phi I a, and then a minus lambda j times identity. Okay, this to the power of rj, where j is not equal to I. I mean, I shouldn't use this j, sorry, let me use k, k, where k is not equal to I. This was phi I a. Remember, that was the definition of phi I a. I erased just now. I mean, this we obtained by the trick. First of all, we took 1 over phi lambda, made a partial expansion, then multiply again by phi lambda, so that you got 1. So it was a sum of terms, and right, this was the expression. So all I did was, I mean, before it was lambda here, I just replaced lambda by a. Right? That was. And what is that? That is again fj a times a product, let's say L not equal to j, a minus lambda j, lambda L times identity to the power of RL. Right? So this is the product. Now you see that if you take the product of these two guys, I mean, what was missing here? This I mean, the jth term was missing here, right? I mean, this product is over from 1 to k, 1 to I think I was calling 1 to k, except that L is not equal to j, right? So here the jth term is missing, but the jth term is here, because you see here all the k's are appearing which are where k is not equal to I. But if I is not equal to j, jth term will appear here, right? Correct? Then that jth term will, if you combine that with this, then that is simply phi of a, right? So just take the jth term from here and put it. You see, you can commute because everything, all the matrices are a or various powers of a. Of course, a commutes with a, right? So ordering doesn't matter. I mean, usually for the matrix you have to keep track of the order. Right? You cannot just move the matrix around. But here the only matrix which appears is identity and A, right? Every term here, right? So you can move it. So you can just take the jth term and move it here. Then this becomes a full product, right? But that was the definition of phi of A. And this Cayley-Hamilton theorem already shows that phi of A is 0, right? identically a 0 matrix. So we can conclude this, we proved that. So when I is not equal to j, this whole thing is 0, 0 matrix. Okay. Now how to prove that, so when I equal to j, we want to prove that phi I square is phi I itself, right? For the second part. Okay. So to prove that, let's take this equation and multiply this equation by phi A. As I said, it doesn't matter left or right, it doesn't, because this commutes. So, so phi A times j equal to 1 to k, phi j A is equal to, what this is saying is this phi A, right? When I multiply by phi A on both sides. Now, in this sum, you see the only term which survives is j equal to I. Because when j is not equal to I, we have already proven that phi I times phi j is 0, right? So in this k, there are k terms here, but the only term which survives is j equal to I term. For that, it just becomes, this is simply phi I square, phi I A square. So we have proven that phi I A square is phi I A itself. Is this like the projection operator, right? Except the projection operator, we also had a definition, we also had the requirement that it was a Hermitian operator. Here we are not saying it's Hermitian, but it satisfies that equation, that phi I square is phi I. Huh? Okay. So again, you see that this looks quite, I mean, it always amazes to me, like when I go through this proof, it always surprises me how, starting from almost empty statements, you know, where phi lambda divided by phi lambda is 1. That was the starting identity. From there, we are able to construct obtain such matrices which have such amazing properties. No, it's quite okay. So that is so we have proved both the statements. So what is the use of this now? So now we'll prove. Okay. So what we are saying here. I want to prove one more thing. You remember we had the sum over phi I A, I going from 1 to k. This was identity matrix, right? So if I take any vector v, right, then I mean this is an operator equation, right? The matrix equation. So I apply both sides on that. So I get here phi I A sum I going from 1 to k. This is the same as vector v. So any vector v I can write as a sum of these k vectors, where each of these vectors is obtained by applying this matrix, particular matrix phi I A acting on v. That is something. Okay. Now what I would like to so let's define the following thing. Let's define a subspace, which I denote by Si, is a subspace of the full vector space S. The full vector space, I mean, was an n-dimensional vector space, but Si is in general some subspace of S, which is given, whose elements can be always written as phi I A acting on some vector v, right? So for all vectors v in S. So I'm defining this Si, the subspace. Okay. So which means that those vectors which can be expressed as phi A acting on arbitrary vector, right, is the set of all those vectors is what I call Si. Okay. It's clear that it's a subspace. You can see that if you can take the sum of these two vectors of this type, it again is a vector of this type. In other words, phi A. Suppose there are two vectors, this and phi A W, both of them belong to this Si by definition. Then the sum of them also belongs to the, right? Or any number, this also belongs to, because this is the same as phi A acting on alpha V plus beta W. So this also belongs to Si. It forms a vector space, subspace. It will be a subspace in general. It won't be the full space, it will be some subspace, subvector space here. Okay. Now, what I would like to show is that these different vectors, I mean, if you take vectors from each of these Si, they are linearly independent of each other. Okay. Remember, our aim is to find a basis. of generalized eigenvectors, right? So I need to look at all these linear independence issues, right? I have to think about that. So what we want to prove that is that if you take the vectors from different subspaces, different SIs are linearly independent. Okay. So so to prove that, so what I want to check is that if I look at an equation like this, phi a bi, okay, summed over I from 1 to k, if I look for this equation, then the only solutions are all the CIs are 0, right? That is a statement of linear independence. The only possible solution is all CI 0. Okay, so how do we do that? It's again very simple, because if you multiply this by phi j, right, phi j of A, then and use this this equation. So in this sum, only term which will survive is I equal to j, because when I is not equal to j, phi j A times phi I A is 0 from this, right? Only term which will survive is I equal to j. In that case, you get Cj, phi j square, but phi j square is phi j. So you find Cj, phi j A, Vj. So let me say that. Let me write it. Otherwise, so multiply by phi j A for some j. This equation. So left hand side just gives me, using this theorem, I mean this result, it just gives me Cj phi j A acting on Vj, right? And that's equal to 0. That's what it's saying. Right hand side is 0. So Cj must be 0, right? I mean, of course, I'm assuming that these vectors are not null. Otherwise, there's no issue of proving linear independence. So if this vector is not 0, then the only possibility is Cj is 0. But that is true for every j. So it proves that each of these coefficients must be 0, and therefore they are linearly independent. So is that clear? Everything? So what we have obtained is that we have decomposed this full vector space S in terms of the sums of this SIs. Each of these are subspaces, and each of these subspaces are linearly independent of the other subspace. So we are saying that this S, the full vector space S, can be actually written as a direct sum of S1 plus S2 plus S3 all the way up to Sk, right? Because we said any vector V, I can write it in the form phi I A P, I going from 1 to k, because we already showed that this was 1. This was identity of, right? So I can just write like that. But then this vector for the I, it is an SI by definition of SI. So I can write any vector V as a linear combination of vectors from this, right? So this is a direct sum of vector spaces. So we have first step is there. Is so far clear the logic? So first step was the Cayley-Hamilton theorem, okay, which showed that the phi of A is 0. Second step was to construct this operator. It was a very constructive thing. I mean, this is actually giving a procedure how to construct these operators, right? These matrices, and those matrices had this very, very important property. Okay? Using this property, we can write any. I mean, this property, and of course, this property that maybe I should just write that down. Phi A summed over I 1 to k. This is identity. Okay. These are the important properties of that. Using this, we can decompose any vector, arbitrary vector, in terms of the sums of vectors from here. And furthermore, all these are linearly independent from each other. Okay. So these are the main statements we have proven. Okay. Now, what we want to prove is that each of these subspaces is in fact the space, the vectors in each of the subspaces are generalized eigenvectors of A, okay, with eigenvalue lambda I. That's what we want to prove now. Okay. So we want to prove that Si consists of generalized eigenvectors, of A with eigenvalue lambda I. So this is what we want to prove now. Okay. If we can prove that, then that's what we were aiming for, right? We wanted to say that you can choose a basis which consists of generalized eigenvectors. Now we already seen that any vector can be expressed as linear combination of this, and that these are linearly independent of each other. Now if we can now show that each of these subspaces consists of generalized eigenvectors, then we're done, right? That's the logic here. Okay, so now, how do we do this? Okay, so let's see. If you take a vector, remember any vector of Si is of the form phi A acting on some vector V, right? By definition, that was the definition of Si, that the vectors of Si are of this form, right? So any vector of in Si can be expressed in this way, right? Okay. Now let's see that. Let's try to. So we want to show that this vector satisfies A minus lambda I times identity to the power of Ri. Okay. Consider this. Let's apply this operator on this vector. Okay. And we want to show that when you apply this on here, it is 0. It gives you 0. So we want to prove, okay, phi A on V is 0. This is what we want to prove. So there's a question mark here. But that is indeed clear, because phi A by definition was Fi. I mean, when we constructed, it was like that, Fi A, and then what was it? A minus lambda j identity product to the power of Rj, where j is not equal to I. Right? Okay. Now, when you multiply by this precisely, I mean, the only term which is missing here is j equal to I. But when you multiply this, that you get the full thing, right? Because this is exactly the missing term, right? But then when you multiply that, this simply becomes phi of A, and then it's 0 by Cayley-Hamilton theorem, right? I mean, so you multiply this. I mean, this was that Fi. Huh? So in this product, only the ith term was missing, but that you are providing now, right? So this is the same as Fi A phi A, right? And that is by Cayley-Hamilton theorem is 0. Right? So it's a 0 matrix then acting on any vector V is 0, of course, right? So therefore, we have shown that this guy satisfies this equation of a generalized eigenvector, right? Okay. Now let me see what was there was one more step here. Yeah. So we want to prove also other way around, right? So what we have proven here is that any vector in Si satisfies this equation. Okay. Now we want to prove other way around, that any vector which satisfies that this acting on that vector is 0 must be inside Si. Okay. So what we have proven here, this proves that any vector of Si satisfies. So this proves that any vector of Si is annihilated annihilated, yeah, by A minus lambda I identity to the power of Ri. Yeah. Now you want to prove the other way. So you want to prove the other way around, that every vector which is annihilated by that is inside here, is an element of Si. So let's consider an arbitrary vector V. I mean, a vector V which satisfies this equation, A minus lambda I identity to the power of Ri equal to 0. So let V be a vector. Let V be a vector which satisfy this equation. Satisfy. Okay. Then we want to prove that this is inside Si. V is contained in Si. And the way to do is that, again, we use this this identity. V is equal to sum over phi A, phi J A, J going from 1 to K, V. Right? This is just I use that this side equation. I mean, apply both sides to V, you get that. Now remember that what is phi J A? Phi J A again is this form. Phi J A is Fj times a product, let's say K, let me not use the K, sorry, L equal to 1 to K, and then A minus lambda L identity to the power of RL. Right, this was phi J A. Yeah. So sorry, L not equal to J. I mean, let me write. This is range is clear, 1 to K. So I will not write that. L not equal to J. Huh? This is what is the definition of the phi J A. But now look at this expression. Any time when J in this sum, whenever J is not equal to I, when J is not equal to I, it will have a term A minus lambda I to the power of Ri. Correct? I mean, you see, the only term which is missing here in this L is the jth term. Everything else appears. So if J is not equal to I is this I. Right? If J is not equal to I, then A minus lambda I to the power of Ri will be there inside. Right? But then that will annihilate the V. Right? So when J is not equal to I, then in this product there will be this term A minus lambda I to the power of Ri will be inside here, inside this product. But then that will annihilate it, because we are saying that the V is annihilated by that. So all those, so in this sum, whenever J is not equal to I, this annihilates V. So the only term which will survive here is just the ith term. Okay? So this is phi A V. Everything else is 0, because the V satisfies this equation. By hypothesis, V satisfies this equation. Right? So every term here will annihilate it except the J equal to I. Right? So we have seen that this V is again an element of Si, because Si by definition was the set of all vectors which can be expressed like this. Right? So we are saying V is equal to that. So this is a complete, we are saying that they are identical. Right? The set of all the vectors which satisfies this equation is identical to the Si, and vice versa. Every element of Si is completely identical. Right. So this proves the okay. Using this, what one can show is that any matrix can be brought into by choosing a basis consisting of this Si. I mean, I have to explain a little bit more on that. But is there any question up to this point? So the logic, is the logic clear? No? So what is the, I mean, say which exactly point is not clear?
How to, when you multiply by J, when you put the J equal I, that's equal to.
Okay, I mean, let's take example. I mean, let's take, I mean, because these i's and j's may be too many. So let's take the I equal to 1. Okay. Let's take, so I'm considering the I equal to 1. I mean, to put some precise, I mean, explicit number, that will be easier. So let's say I equal to 1, and let's suppose there are only 3 terms, k equal to 3. There are only 3. So we have, so let's say phi1a is f1a times a minus lambda 2, because remember in this sum, in this product, this number is not appearing, right? So since I'm looking at the phi1, 1 should not appear here in this product. So lambda 2I to the power of R2 times a minus lambda 3 to the power of R3, right? Now phi2a is f2a. Now the 2 will be missing in this product. So it will be a minus lambda 1 identity to the power of R1 and a minus lambda 3 identity to the power of R3, right? And finally phi3a will be f3a times a minus, now the 3 will be missing, so a minus lambda 1 identity to the power of R1, a minus lambda 2 identity to the power of R2, right? These are the 3. I'm considering this k equal to 3, so there are only 3 terms. Now consider, so suppose there is some vector v which satisfies this equation, a minus lambda 1 identity to the power of R1 acting on v is equal to 0. So suppose that some vector which satisfies this equation. Then we want to show that this actually belongs to the S1. That's what we want to try to prove. So then we use this fact that anyway, I can take this vector v. I mean, so I'm just trying to. I use the fact that phi1 plus phi2 plus phi3 is identity matrix. This equation, right? So then we can write v is equal to phi1a acting on v plus phi2a acting on v plus phi3a acting on v. I can write like that. Now look at these terms. Both the phi2a and phi3a contains a term a minus lambda 1 to the R1, right? But by hypothesis, v is satisfying this equation, right? So both this is 0 and this is 0, because both of these operators and both of these matrices contain this factor, and that factor annihilates by hypothesis, right? Is it clear? Okay. So then these two have disappeared, they are 0, so what is left over is that. Therefore, this implies that v belongs to S1, because S1 was a set of all the vectors which could be expressed in this form, right? Okay. Can I proceed? Can I erase this part, or do you have any questions? So I erase this now. Okay. I'll keep this anyway. Okay. Okay. And now let's look at more carefully some SI vectors. We said the SI vectors. I mean, what all this is proving is that every vector of SI satisfies this equation. A minus lambda I identity to the power of Ri equal to 0. But of course, this does not necessarily, so this will be some generalized eigenvector of A with eigenvalue lambda I, right. But the rank need not be equal to Ri, right, because to have a rank Ri, we should also have that this to the power of Ri minus 1 is not equal to 0, right. Okay, it could be there a rank Ri itself, but it may not be also, right. But it is clear that I mean, if V itself is not non-trivial, I mean, if we are always assuming that V is not a null vector, otherwise there is nothing to discuss about, right. I mean, this is a triviality then, right. So V is not null. Okay. Well, what is the A minus lambda I times identity to the power of V? There are two possibilities. Either this is null vector or is not a null vector. Okay. If it is null vector, then we are saying the rank is 1, right? If this is null. I mean, there are two possibilities now, right? One, it is null, which means that this is 0, or second, not null. Only two possibilities. If it is null, then V is the ordinary eigenvector, which means of rank 1, right? If this is null, then it's a rank 1 vector, rank 1 eigenvector. If it is not null, okay, let's go ahead and apply A minus 2 powers lambda I 1 to the power of 2 acting on V, right? Again, two possibilities. So if it is not null, then I look at that. If it's null, then I stop. There's nothing more to do. If it's not null, I go here. Then again, there are two possibilities: if this is null or not null. Okay. If it is null, then this is of rank 2, right? Because this is null, but this to the power of 1 was not null. That was the definition of rank, right? So it's rank 2. If it's not null, continue, go to the third step, and so on and so forth. But so whatever the rank of this vector is going to be something between 1 and Ri, because at the level when you reach Ri, it is certainly 0, right? So this V will have a rank, which is be greater than between 1 and Ri, somewhere between 1 and Ri. Right? Okay, so that will be its rank. Okay, so suppose the rank of this vector was, well, let's say mi. Okay, so suppose this rank was equal to mi. I just call it mi. Okay, then let's consider the set of vectors V, A minus lambda I identity, V, all the way up to A minus lambda I identity to the power of mi minus 1, right? Consider these vectors. Okay, they are all non-null vectors, because we are saying by definition rank is mi. So any power less than mi will not annihilate it, right? So they are not null. None of these vectors is null vector. Okay. Now the one thing you can prove is that this set of, so how many vectors are there? There are mi vectors, right? V 1 power all the way up to mi minus 1. So altogether there are mi vectors here. So one thing you can prove is that the set of these mi vectors is linearly independent. Okay, they are linearly independent. The proof is very simple. Again, if you take suppose take the combination, so we have to look at basically this equation, right? C, let's say Cj, A minus lambda I identity to the power of j acting on V, and j going from 0 up to mi minus 1, right? I mean, this j equal to 0 means that, j equal to 1 means this, j equal to 2 means and finally j equal to mi minus 1 is that. So this is a linear combination of these mi vectors. So we are looking at this equation, that this is equal to 0, and we want to see whether there are non-trivial solutions for Cj. If there are non-trivial solutions, I mean non-zero solutions for Cj, then they are linearly dependent, and if the only solution is Cj equal to 0 for each j, if the only solution is all these coefficients are 0, then they are linearly independent, right? That's what we want to check. Well, so let's do the following. Let's multiply this equation by A minus lambda I times identity. Let's multiply that. Okay. No, in fact, let me do the following. Let me multiply this by mi minus 1. Multiply this equation by that. Okay. Then you see the only term which will survive is j equal to 0, because let's take j equal to 1 term. J equal to 1 means this has already 1 power. I am multiplying this by mi minus 1, so then it becomes, I mean, this to the power of mi minus 1, then it becomes power mi, but that annihilates it because the rank is mi, right? So similarly, for any value j greater than 0, j equal to 1, j equal to 2, etc., the powers will be greater than or equal to mi, and therefore it will annihilate it. So the only term which will survive here is just the j equal to 0 term, which means C0. So the left hand side simply becomes C0 times A minus lambda I identity to the power of mi minus 1. This is the only term which survives here, right, on the left hand side. And that's supposed to be equal to 0, because this multiplying that 0 is 0, right? So this, and since I know that this is not a null vector, so C0 must be 0. Okay. So then the sum starts from j equal to 1, because C0 is 0, right? Now multiply by mi minus 2. Okay. So then only term which will survive is j equal to 1, everything else vanishes. So then you have an equation C1 times this to the power of 1 to the power of m minus 1 is 0. So C1 must be 0. So then this sum will start from 2. Then you multiply by mi minus 3, you know, and so on. So this way, it's just step by step, you prove that all the coefficients must be vanishing. Okay. So the only solution is all the Cj's are 0, which means that they are linearly independent. Okay. So in general, in this, okay. So we said already that every vector here satisfies this equation, right? Now that vector may have different ranks, no? Ranks, all the ranks are going to be between 1 and Ri, right? But there could be many different eigenvectors, many different generalized eigenvectors of different ranks, right? So the structure is a bit like this. So this Si, you can choose a basis in this Si. So we can choose a basis in Si consisting of vectors of the following type. So I have got some, let's say V with rank, say mi, let's call it V1, with rank, say mi minus mi1. Okay. Then there is another vector V2 with rank mi2, and so on, right? Because it can have different, I mean, different vectors with different ranks. No? For each of them, I can construct mi vectors which are linearly independent like that. So mi1. So the basis I can choose is the following. I choose, so the basis will be V1, then this A minus lambda I V1, all the way up to that A minus lambda I identity to the power of m I 1 minus 1 V1. Okay. Then I start from V2, and again take this various powers V2 all the way up to A minus lambda I identity to the power of mi2 minus 1 V2, and so on. Okay. So this way we can choose a basis for this entire subspace Si. Okay. And we do that for each Si. We keep choosing such basis. Then let us try to see how the A looks like in this basis. Okay. So first of all, I should have mentioned that first statement is the following. A acting on A maps Si to Si. Yeah, sorry. This is not very clear, right? V2. And this power is whatever the rank minus 1, right? because if you raise it to the power rank, that is 0, right? So then you get a null vector, but these are not null vectors. Mi2 minus 1, minus 1 v2. Okay, and this way you can choose some bases like this. There are mi1 of these vectors, mi2 of these vectors, and so on, whatever that. Of course, the total number should be equal to the dimension of the SI, right? Whatever the dimension of SI is, this total number of linearly independent vectors must be equal to that dimension. Okay. So let's see if the I want to show that A maps SI to SI. Okay. That already means that A will be of a block diagonal form if you choose the basis like this, right? Okay. So I mean, yeah, okay. So let's prove that. So remember, any vector of SI, so arbitrary vector of SI is of the form phi A acting on some vector V, right? That was the definition of SI. Okay. Now let's apply A on that. Well, A commutes with the phi A because all the matrices here are A and identity. So this is the same as phi A acting on A acting on V, right? Okay, this is some another vector, right? But again, since this is phi A acting on some vector, this again belongs to SI, right? So it says that what it shows is that A acting on an arbitrary vector of SI will again be inside SI. Just not obvious, right? It's not trivial because after all, the full S is the sum of SI, direct sum of SI, S1 plus S2 and so on. Now, of course, A takes a vector of S and brings it back to S, but that doesn't imply that if A acts on S1, it will come back to S1. It could have gone to S2, no? But what this is showing is that no, if A acts on S1, the result will again be a vector in S1. Yeah, this is a so if I choose a basis, so let's say I choose a basis like this. So I have the first. I mean, suppose each of this SI have some dimension. I mean, I don't know, give some name to it. Some dimension. Suppose the dimension of SI is Ni, let's say. It will be some in some dimension, some finite dimension. Of course, sum of all these Ni's will be equal to capital N. So that's a full dimension space, right? Yes. Now, so let's take the first N1 of these vectors and arrange them here. So this part will be for the S1. Then the next will be N2. So this will be S1, this will be S2 vectors, and so on. I choose that. Now when I apply A is this big matrix and capital N by capital N matrix. When A is so suppose I am looking at vectors with non-zero components only here. Everything else 0 here, right? That means it's a vector inside S1. Then what this is saying is the result will again be a vector in S1, right? So when you apply A on this thing, it will again have only the first N1 entries non-zero, right? Similarly, if you take a vector with only the non-zero entries only in this N2, this guy, it will again go back to S2. So it will be again non-zero only in the second block, right? So that means the A must be in the block form. So this is N1 by N1, this will be N2 by N2, everything else 0. Okay. So this is a block structure which appears. So you have already done kind of choosing this basis. You have already done some partially. I mean, you see there's already some partial diagonalization, but not completely. Now let us look at individual block here. Now let's look at, for example, S1 block. I've chosen the basis like this for S1. Okay. So what is it going to do? So let's look at this V1. Let's look at what happens to. Let's take the V. I mean, I'm looking at. So let's look at the A acting on V1. Okay. Well, this I can rewrite it as A minus lambda I 1 V1 plus lambda I V1. I mean, I just added and subtracted that. Okay. But this guy is that next vector. And remember, this is linearly independent to that. this is another vector, but this guy is the same vector. Original. So the form, when you look at the A acting on, so let's look at this, let's expand. I'm just expanding, say, one of them, ith guy, and you're trying to see what is happening in that block. So in that block, I take the vector, again I arrange, so V1 A minus lambda I times V1 acting on V1 identity, and so on, right? This to the power of 2 acting on V1 all the way up to this to the power of whatever the rank is, Mi1 minus 1 acting on V1. So I choose this basis in this. So I arrange in this column vectors in this order. Now, when A acts on this, say this vector, or in fact any vector, let's look at A acting on any vector, A acting on any of these vectors. So any of these vectors are what? A minus lambda I times identity to the power of some, let's say, L acting on V1, where L is between 0 and Mi1 minus 1, right? All these vectors I can write like that, right? Where L is between this, L equal to 0 here and L equal to Mi minus 1. Yeah? But when I apply that, again, let's do the same thing, add and subtract this piece. So you get here A minus, when I add, so this is same as A minus lambda I 1 plus lambda I times 1. I just added and subtracted that. Times this same vector, A minus lambda I1 to the power of L V1. Correct? And nothing, I've done nothing. But now take the first, this combination with that raises the power by 1. So this gives you A minus lambda I1 to the power of L plus 1 acting on V1, the first term, this term, and then plus lambda I times V1. Okay? So this is general structure. So you see this pattern. What it is doing, when it acts on the Lth guy, it gives you back the Lth guy with a number lambda I, with the, right? Plus it another vector which is the L plus 1th guy, right? So in this basis, how will the A look like? A will look like, there will be a diagonal entry, because remember this is the same vector, the Lth vector which is coming back. So there will be a diagonal term which will be, diagonal will be lambda I. In fact, all of them will be lambda I. You see, this is independent of L. This is the same constant. So all the diagonal will be lambda I, and there will be off diagonal term. You see, because this is not the same vector. I started from Lth vector, I pushed to L plus 1th vector. Okay. So then there will be, so for example, if L equal to 0, then I will get here, this will be 1, right? So from here you go there, from here you go there, and so on, right? So one step. It's just pushing you one step. So that means there must be a 1 here. Okay? And the coefficient is 1. Okay? So just one diagonal lower than the diagonal, you will have 1. Everything else 0. Okay? Everything else, upper block is completely 0. Okay? And the lower block is just lambda I is the diagonal, and 1, 1, 1 in the, just below the diagonal, all the way up to here, and everything else 0. Here is all 0. So in this, once you choose this basis, you see the matrix A has become like this basis, right? It's not completely diagonal, but it's the closest that you can get. And so, but this is, you see, this is what is happening. This is the rank was, there are Mi1 vectors here, but Mi1 was a rank. So what we are seeing is that there are these blocks, this Mi1 by Mi1 blocks, where the matrix can be brought into this form. Okay? And then of course the full matrix is like block diagonals, no? Because we already said Si is mapped to Si, that's already giving you a block diagonal. So this is the structure of the matrix A. Yeah, when L is equal to the highest, the possible number, this number, then you see here you will just get Mi1 but that will be 0. So it stops there. It doesn't go beyond it because rank is mi1, so that is 0. So that's why this is a structure. In particular, it shows that since I know in Hermitian operators, in Hermitian matrices, for Hermitian operators, all the eigenvalues are ordinary eigenvalues, so the rank is always 1. So this proves to you that if you choose that basis, this basis the way we are doing, since all the rank is all 1, this is all just 1 vectors here. So this is diagonal already, right? So if rank was 1, there is no problem. It's diagonal. So this is the reason why Hermitian operators can be diagonalized completely. Okay. The only thing I need to show now is the dimensionality of these different eigenvalues. How many times lambda I appears? So for this, so let's see. So this way, remember we said SI I decompose in terms of different vectors. So I don't know. Now that I'm running out the symbols here. I don't know V1, V2. So this is our rank. Say mi1 minus 1, mi1, this rank mi2, and so on. And then say let's say maximum, let's say it will be some finite number anyway. Let's say VL, this will have some MIL, right? So for each of them, I have this mi1 linearly independent vectors here by these powers, I mean increasing powers, right? These things. These are linearly. For this guy, similarly starting from V2, I construct another mi2 linearly independent vectors, and so on and so forth, right? So it's clear that what is the dimension of SI? Dimension of SI is simply the sum of these numbers, right? So dimension of SI is a sum mi say j, where j goes from 1 to L, right? Because this is a basis. This forms a basis for these vectors. These vectors form a basis for that. So that will be the dimension. Now, so let's compute. So let's look at. So what I want to show is that this dimension is in fact equal to Ri. This is what I want to show. Okay. So there's a question mark here, where Ri was what was appearing in the characteristic polynomial. Okay. So to show this, yeah. So let's. So let's compute the determinant. See, determinant, as we saw, determinant is independent of the choice of basis, right? We remember we said that even if you change the basis, determinant doesn't change. Last time we proved that determinant was a scalar kind of. I mean, it doesn't transfer. Even if you change the basis, determinant remains the same, right? So in particular, let's compute the phi of lambda, which is the determinant of lambda minus a, lambda times identity minus a, right? In this basis that we have chosen. This is, by the way, this is called this basis is called canonical Jordan form, canonical Jordan basis, Jordan form. This is a canonical choice of basis in which you can bring the matrix in this form. Remember what is the characteristic of this matrix? Diagonals are all lambda I inside the SI space, and there, at most there will be some off diagonal numbers, but just one diagonal lower, right? Upper half of the triangle, this is 0. Upper half triangle is 0. In the lower half, you can have 1, 1, 1. If you have a rank higher than 1 eigenvector. For rank 1, there's nothing. It's just diagonal. So let's compute this determinant in this basis that we have chosen here. But in this basis, it's clear you're just going to get the products of, upper part is 0. So if I compute determinant, I'll just get lambda I to the power of this number, whatever the dimension of this matrix is. This will not enter in the determinant, right? Because everything else up here is 0. Right? That's clear, right? You just compute the determinant of this one, let's say. Suppose this happened to be 4 by 4 matrix. Just take an example. Suppose it's 4 by 4 matrix. Then, so you will compute. So it will be you open along this row. So it will be this times the determinant of that 3 by 3. Now open this to compute this 3 by 3 determinant. Again, take this row. Then it's lambda 1 times this 2 by 2 matrix. Then again, so you see that's only the product of these diagonals. This doesn't enter. These lower guys don't enter in the determinant computation. So this determinant in the you do it in this number, it will be simply let's compute determinant of A itself. Compute determinant of A. Okay, determinant of A, or okay, let's do this lambda minus lambda I, lambda minus A. So I will get this lambda times identity. So this will become lambda minus lambda I. No, here the diagonal will become lambda minus lambda I, because I'm taking lambda minus A. This is A matrix. Okay. So I will get here lambda minus lambda I to the power of dim Si, right, and product over I going from 1 to k. That's what I will get in the when I compute it in the Jordan basis, right? But we already saw this is independent of the basis, so that is the answer, right? But we defined the phi lambda. Remember how we defined the Ri? Ri was simply this, the power of lambda minus lambda I, right? So that proves that dim Si is the same as Ri. Dimension of each Si space is Ri. So that explains to us what is the meaning of Ri. Ri is a multiplicity. How many? I mean, we of course knew it anyway, but this is proving that concretely, right? There are Ri, these Ri dimensional spaces, Vi. Okay, I think that basically finishes this. So what we have done. So this is the general form, but applied specially to the case of rank 1, if all eigenvectors of any matrix A are ordinary eigenvectors, are of rank 1, okay, then this also implies that we can diagonalize. We can completely diagonalize. Diagonalize A. If there are some eigenvectors are higher than rank 1, we cannot diagonalize completely, but we can bring it into this form. Right? In particular, Hermitian operators. For Hermitian operators, since all the eigenvectors are of rank 1, this can be diagonalized. So we can diagonalize it. Finally, let me just the last five minutes I just explained to you precisely how to do this. I mean, a very convenient way of doing it. So let's choose. Let's find all the eigenvalues. So the steps in doing this. How do you do this, Hermitian operators? What you do is first of all find out all the eigenvalues. So compute determinant of this. Let's say h lambda I minus h. H is the Hermitian operator. Compute that, and from just read off from this. This will be some polynomial. It will be of this form. Okay? Product I equal to 1 to k. It will be some form. Remember, when we say rank is 1 for Hermitian operators, but it may still have Ri may still be not equal to 1. You see, you can have degeneracy even in the Hermitian operators, right? Same eigenvalue may appear many times, no? But it's just that what we are saying, they are all rank 1, right? Okay, so we do this, and then for each of them, I find the eigenfunctions. So you find the eigenfunctions. Let's say Vi of some lambda I. Let's call it Vi P. Let's say Vi P will have eigenvalue lambda I. Okay, and P will remember how many times this appears. Remember the dimensionality of this space is exactly Ri. So this P goes from 1 to Ri. Right? That many times this eigen. So the subspace with this eigenvalue is dimension Ri. Si was dimension Ri. So there will be Ri vectors here. Right? Ri linearly independent vectors. Now we already know that we already proven that if you take two eigenvectors of a Hermitian operator with different eigenvalues, they are going to be orthogonal to each other. So, the vectors of different SI subspaces, they are orthogonal to each other. That is one thing. Now, within each SI, of course, there is nothing which tells you it's orthogonal, but you can always use the orthogonalization theorem, I mean the procedure, Graham-Schmidt procedure, to find an orthonormal basis inside each SI. So, we can choose all of these VIPs to be orthonormal. This you can always do. This is whatever, some finite dimensional space, Ri. So, you can just choose in some orthonormal basis inside here, right, Graham-Schmidt. And the different SI vectors are anyway orthogonal to each other, so you don't have to do anything, right. So, choose VIP such that they are orthonormal. So, choose them, choose this so that they are orthonormal. Okay. Okay. So, now how do we construct? So, what I want to do is that I want to explicitly construct the matrix, the transformation which makes H diagonal. I mean, to begin with, H was not a diagonal matrix, just some Hermitian matrix, but I want to now construct explicit matrix which will make it diagonal. And then I will stop here, I think. Yeah. So, the procedure is the following. Now, construct. So, remember, each of these vector, this is say n by n matrix, right. So, each of these vector is a n column vector. So, let us construct a big matrix, and I call this matrix U in the following way. So, first I put here the first column, I put here, let us say V1 1, okay. So, this is a column vector, remember. So, I take I equal to 1, P equal to 1. The second one I put V1 2, all the way up to whatever the multiplicity of that is, V1 R1. Then I go for the V2 1 and so on up to the. So, this way I just arrange them. Now, remember the sum of all the Ri's is equal to n. So, this way you have n, exactly n vectors, capital N, right. Remember, sum over all Ri equal to capital N. So, this way you have n vectors here. Each of them is an n column, has n entries, is a n column vector. So, this will give you a U n by n matrix, right. Okay. Now, let us multiply this with the H on the left. So, let us multiply now. Let us consider H times U. H times U. What am I going to get? So, this is the same as, I mean, remember H is a n by n matrix. So, first let us look at the first column here. I mean, this will be also n by n matrix. Look at the first column. The first column here, if you look at the first column here, this first column is obtained by applying H on this first column, right. But this was an eigenvector of H, right, with eigenvalue lambda 1. So, what I am going to get is simply lambda 1 times the first column, right. In the second column, it will be lambda 1 times the second column. So, lambda 1 times, so this column will be lambda 1 times V 1 1. Then it will be again lambda 1 times V 1 2 and so on. And finally, then when you come to the V2 guys, it will become lambda 2 times V2 1 and so on, right. Because the second column is the same as H acting on the second column. This column will be the H acting on that, which gives you lambda 2 times that, right. Okay. Now, I think I need to prove one more thing. I want to first of all prove that this is a unitary matrix. Okay. This is a unitary matrix, which means U dagger U is equal to identity. But that's obvious, because when you take the U dagger, what you're going to get? You're going to get these column vectors will become row vectors, and you have to take complex conjugation. Two things I have to do, right? You take a dagger. Now you multiply. So, multiply the U dagger. So, let me write down, I can erase this part now. So, what is U dagger? So, this will be just the complex conjugate of so this first column has become the first row. and this is going to become simply V1 1 bar. I will take the complex conjugate. The second one will become V1 2 bar, and so on. Now multiply U dagger with U. Okay, the first column with the first row with the first column is just the norm of this, which we have chosen orthonormal basis. So that is 1. This one with the second one is 0 because it's orthogonal to each other. So everything else will become 0 except the first row with the first column. So that will be the diagonal entry 1, right? Now take the second row, and again same thing. Second row with the first column is 0. Second row with the second column will be 1, and with everything else 0. So you see that U dagger times U becomes a simply identity matrix this way. This is always the case. If you arrange them to be orthonormal vectors, these columns to be orthonormal vectors, then the corresponding matrix is a unitary matrix. So that's fine. So if I now want to apply U inverse on this, U inverse is the same as U dagger, right? Because unitary. So H times U was that. Now I apply U dagger. So for the same reason, you see this times that is non-zero, but it's not equal to 1, but it's lambda 1 now, right? This times the second column is 0 because orthonormal, right? So this whole thing, you can immediately, just convince yourself by this reasoning that what you will get is simply lambda 1 in the diagonal, R1 number of times, right? So there will be R1 number of lambda 1, R2 number of lambda 2, and so on, and so on, and completely diagonal. This is how, right? So this is the way to construct the unitary matrix is to find, and one way to do that is to find all the eigenfunctions and choose an orthonormal basis. Orthonormal basis consisting of eigenfunctions. For the Hermitian operator, it's always possible, right? And then use them to construct the unitary matrix which transforms. In practice, of course, it's very difficult. To find eigenfunctions is not an easy thing. Apart from some small, maybe 2 by 2 matrix or 3 by 3 matrix, you can explicitly work out. But for large matrices, it becomes very difficult to. Right? But this is more a question of principle that you can diagonalize.